the legs. Okay, and down here you have something like this, and you have it was fixed here. So this suffers an axial motion, right? Here we have a one story, second, and the highest. Now, let's suppose that on this side, probably you have it on the other, but here I have a strain gauge, okay? And this measures, of course, the strain as function of time. Okay, now, in our model, we said that we were going to represent this as a spring. But this is spring, you know, that acts in this direction. We have a K equivalent. Okay, now, this is what you have to do, okay? Do you remember the expression for the equivalent K? Anybody remembers the equivalent, the equation for the equivalent K? Anybody? No?
¿En serial o parallel?
No, for a single spring. Okay, what you had to do, remember, is to consider the beam, and this is a model that civil engineers use, okay? This is a beam, and up here, since it is well connected to the first story, they assume that this is guided, okay? So you have something like this. Okay, so this is welded, welded, welded. Okay, now here, if we have a system, let's use a reference system like this one. So this is X. This is, suppose this is Y. Okay, so to calculate the stiffness, what you have to do is you apply a force here, okay? And this is going to deform like this. Here, since it is welded to this little square that moves in the horizontal direction, but since it is welded, there is no slope, okay? So the end of this beam kept straight, keeps vertical all the time, okay? Now, we can go on and say that at X equals to 0, it is clamped. And at Y, X equal L, it's guided. So you can check the boundary conditions for each one of those cases, okay? And if you integrate, what's going to be of P of X in this case? Anybody? P of X.
0, doctor.
There's nothing, right? So from here to here, there's nothing. Okay? So for the boundary condition in the guided, since you are applied a force F, that force F has to be considered in the boundary condition. So this is not an homogeneous problem, okay, because you have a value F. Now, if you integrate twice, so you can calculate something like this. So here, this is the bending moment. Okay, so you can estimate, you are analyzing from here, so you are analyzing this. So this point here, when you have located the strain gauge, you know the distance from the bottom to the position where the strain gauge is located. So you can evaluate that. Let's call M then at the strain gauge. Okay. Okay, now, similarly, so you integrate 2 more times. So you have, this is ax cubed over 6 plus bx squared over 2 plus cx plus d, right? So you have this, and now you are able to calculate this, right? Now, what you can do now is this, okay? To evaluate this, the bending moment, in here, you need the force. How much is the force? Well, here you can evaluate it, because you can say that EI sub C delta, this is equal to who is this value? This value is the motion direction. So, and this is the displacement of the mass that you have here. So this is U1, this is U1, e to the I omega t. So this is this one here. So after you do this, in here you have F. So from here, you can calculate, let's call it F1, because it's from the first story. Okay, so F1 is calculated using U1. So that's the force that you need to apply in here in order to make this to move a certain distance U1. Once you know that, you can calculate the moment. Now, what will be the next step in order to compare with experiment? Ms. Gutenberg, what would you do next after you know the bending moment? No? Mr. Ramon? Yeah, go on.
That?
I couldn't understand. We're having trouble with your audio. Mr. Ramon, can you help us? We know the bending moment. What do we do next? We need a strain, because in the experiment, see, all of these people, all of this is theoretical. All of this is theory. In your homework number 1, you calculated U1. So U1, which is V of L, you know it. You have Young modulus of the steel, you know the inertia, the length, so you know everything except F1. With F1, you put it in here, you can calculate the bending moment. Now what, Mr. Ramon? What next? Plano, can you help us? What do we do next?
No.
No? Anybody?
Doctor, is
Normal
next
strain.
step is possible
Stress, yes.
calculate this.
So we
load.
calculate normal stress, but now this normal stress depends on time. Why? Because this is not a constant, because this is moving. It will be minus mz y divided by h. And finally, divided by
Young models.
Yes. So all of this is theory. This is the theoretical side. So if you know the response from homework 1, calculate F1, evaluating this, the expression for the displacement at the end at L, and replace V at L by U1, the amplitude. So you have this and go on. So you are able to calculate the strain. You have to compare that with the experiment. Okay. Similarly, we can do an analysis for the second.
Doctor, but for the second one, the boundary conditions change, right?
Yeah. For the second one, what you can do, I'm going to change this, people. I don't know how to generate a new one on here. Okay. What happens for the next one? Okay. So let's suppose that this one, let's suppose is the forms like this and goes up to here. Let me change color. So the next one is like this, comes like that. What we can do is we can take this point as X and this as a Y. How much is this one here? Mr. Zamora, how much is this?
Is U2, the other is 2.
This is the original. This is the static equilibrium. This is U2. This is U1. How much is this? Anybody?
U1 plus information.
2 minus U1. Now here we have to be careful. Why? Because these two amounts are similarly for the last step. We have to be careful because the if you consider the two the return. Oh, here it is. Okay, here is K equivalent has to be twice because the two legs are acting together. Okay, it's like having twice the inertia.
Victor, I have a question because
Yeah, go on.
we have one data from the base, but how can we analyze this data? Because we had 4 strain gauge, one from the base, the first union, the second union, and the top.
Okay, so you have one here, right? And you calculate this using these relations. You have another here. Okay. But you can calculate in this for the second beam, you can also calculate the bending moment. exactly the same. The only difference is that instead of using U1, you have to calculate the difference between the two.
But,
So,
but in the experiment, we have 1 under the EX1.
yeah, but you tell me what it is. I mean,
I think
if
that it will be 0 because the base is clamped, I think.
no. Remember, every time you have a clamped end, you have very large strain. I think you have here one, right? The second was here. The third was here. What was the last one?
In the base.
Here? Like this?
Yes.
Yeah, but now for this one here, you can evaluate the bending moment at a very low value. So in this case, this term will be small, and you can have B. Okay, so you have the bending moment here and the bending moment here. Probably the values of these two in some cases will be different, because you see here in this situation, Mr. Zamora, the strain will be positive or negative here.
Positive.
Yes, and here,
We almost 0. But I think it's positive too.
to have zero bending moment, what type of support do you have? Zero bending moment here. What type of support do you need?
Simple support.
Simple support, yes. But in this case, it's not. Maybe you get confused because let me put it horizontally. This is your beam. It's guided. Let's have a positive force here. So this is going to deform like this. In this case, you have positive bending moment because it's smiling. In this case, you have negative bending moment. So the bending moment probably is going to be like this. So if you put it in a strain here, you're gonna have compression. If you put it in a strain gauge here, you're gonna have tension. Questions, people? Questions?
Yes, doctor, I have a question. But in the assignment number 1, we calculate the amplitudes, right? And now you
Yep.
tell us that we have to compare the strain.
Yeah, but as I said before, here, okay, this is the amplitude that you calculated, which is this motion.
Yes.
It horizontally, this case, okay, this is going to be you. In this case, it's going to be your U1. So you have this value already. So you have this value. You need to go on and calculate. From that point, you need to calculate the force. So in this case, you would have to calculate the force that it is required to produce this deflection, basically.
Yes. But what about the accelerometer?
Oh, okay. Let me close this. Are we clear with these people? Are we clear so far? Okay, now, what about the accelerations? Oh, here. Okay. You have this motion, you call it U1, right? This motion, it's U2. And this one here is U3, right? And each one of these, you express it like this. Now, tell me, let's suppose I have an accelerometer here, very close to the first story. So basically, this acceleration is the acceleration of U1. Can you calculate the acceleration of U1? Ms. Vega, can you calculate the acceleration of U1? Mr. Carrillo, can you calculate the acceleration of U1?
Yes, I I save in my other computer, doctor. I don't open
Oh,
this.
come on. Explain to me how you can calculate.
I don't remember the value, doctor. Is the change the for gravity? They tell me the engineer.
The dividing side.
Zambrano?
The dividing side is minus the frequency square. Yeah.
What is this? The amplitude of the acceleration. Zambrano?
Yes, doctor.
Similarly for the other, similar for the other. So you have this, and you calculated that for a certain frequency. So you can calculate the acceleration, the amplitude of the acceleration. Group one, who is in group one? Who is in group one, people? Turn on your cameras, please. Turn on your cameras. I would like to see your faces. Turn on your cameras. Okay, who is in group one, people? Who is in group one?
I'm Doctor. I'm Ronnie Matute.
And who is working with you?
Ronnie Matute.
Matute. What is Matute? Oh. Who is Matute? Raise your hand, Matute. Not here. See any Matute here? Oh, okay, okay, I know. Not here, right? It's only two people for your project?
Yes, Doctor.
Okay, group two. Who is in group two? Who is in group two? Nobody's in group two? Come on, man. Nobody in group two? Jesus. Group three. Who is in group three?
Me, doctor.
Me, Dr. Sayo, Zamora, and Barba.
And Barba. What is Barba? Who is the chief? Who is the chief? Who is the responsible for that? Who is the person in charge?
Me, Doctor.
Who elected you? Who elected you? Zamora, you elected her to be your boss?
All group elect to Daniela.
Okay, group four. Who is in group four?
Me, doctor.
You work with?
And Ramon, but he had all the class.
Okay, so that's only two people.
Yes.
Okay, group five. Vega. And who you work with, Miss Vega? You work alone?
Matías
Atia, okay.
and Enrique.
Enrique, okay. So Matias and you're from outside. So you group number six, number seven.
Hi, doctor. Me, Iñiguez. Only group 2 persons.
Okay, good. 8. Group 8,
Freire, Pincay, and Jimenez.
Freire, Pincay, and
Jimenez.
Jimenez. That's a pachanga. Too many people in there.
Doctor, we are group number 2. We didn't know that. We can come to.
Okay.
Me, Delgado, and Hidrogo.
No. Oh, okay. Delay. Okay. So, who's missing? Group 9?
I think that there is a confusion because we supposed to be group number 7 with Michelle Lopez. So I don't know.
Giovanna, please organize this, okay? So everybody knows his or her number, okay? Who's missing? No, that's all, right? We have all of them. Okay, people, let's start working because this is due next Friday. And on that day, I will give you the assignment for the next assignment because we need to work on this. Now, about chapter 3, we're gonna do 2 homeworks, okay? 2 homeworks because this is such a long chapter. So we have to complete that. And the second one, it's due the day of the evaluation. Okay, so we have no time for waste. Yeah, somebody had a question. Any
Doctor,
question?
I have a question. It's about the amplitude. When we did the assignment 1 or
Okay.
2, I don't remember. We obtained only 3 amplitude.
Yeah.
U1, U2, and U3, but we have 4 string gauge. So we are a little bit confused with that because at the end we are going to have other amplitudes, right?
Can you see my screen?
Yes.
The white screen? Yeah. Okay.
Yeah.
See, the thing is this, in the lower leg, in this leg here, we could have the strong. Okay, let me put this in the horizontal position. This thing here. So this moves like this, and this is U1 of T, right? So you have one string gauge here, string gauge here. This is X, and I'm going to plot the bending moment for this leg only. And the bending moment, we said that it was like this. So you want to calculate this, the string in here, so you evaluate the bending moment in here. You want to evaluate this string, you evaluate the bending moment in here. So for the same leg, you can evaluate the bending moment here, the bending moment here, and in every position, you can calculate the stress and finally the strain. Sayo?
Yes, but when you explain about how can we obtain the moment in U1 using U1, you put the deformation, the deformation V is equal to U1, okay?
Yeah.
For obtain in that part, but in the lower part, how value can
No. Oh, hold on. I obtain F1. So that's the force that you have to apply here in order to have this deflection. After you know F1, you can evaluate the bending moment. And this is what I'm showing here. The bending moment is here. And this bending moment is connected to F1. And this F1 is connected to U1. And this is something that you have. So if you have F1 in this end, then you have this value of force and this value of bending moment, then you're going to have here a certain strain and a different value in this position. So for every value of U1, you have one strain here and another different strain up here. So you have two values.
Okay, doctor, I understand now.
I'm glad. Any other question, people?
Doctor, I have a question.
Yeah, go on.
The program give us data.
Yep.
What we use this data?
The program gives you strain. So, and you are calculating strain. So you can compare the two directly. So you have for different time, you have different values of strain.
And we don't have a calculated acceleration, right?
Yeah, now that's one thing. The other thing is that you have to compare the acceleration. Yes, in that case, you have to be careful. Why? Because the accelerometer gives you millivolts, and you have to convert that to G's.
And doctor, in the doc say that the homework is to Friday.
Don't change the subject. Right now, I'm trying to explain you if you can convert volts to acceleration. Yeah, let's solve that first. Okay. Are we clear with that? So the values of the strain you get directly from the strain gauge, and you can compare that with the theoretical. The values of the accelerometers, we have to be careful because those are millivolts. You have to convert that to meters per second square. Yeah, you have to talk to Engineer Isaac for the factor for conversion. And then you have strain, you have acceleration, and you calculate them. And you hopefully they will be close. That's one thing. Now, what was the second question?
In the doc say that the homework is for Friday.
Yeah.
And in the aula virtual say that it's for Thursday.
It's for Thursday.
It's for Thursday.
I'm sorry, it's for Friday, right? At midnight.
Okay. And the third question is for the wave.
Too many questions. Well,
for the wave. Because I tell with the title, it say that it's shallow water. But when I do the calculations, the K for H is for deep wave, no shallow waves. It's for deep wave.
Okay, I was talking to Ruben about that topic because he is a hydrodynamicist. I am a structuralist, remember? And I was asking him if he considered that water depth to be shallow, and he wasn't sure. So what I suggest is get the results for shallow water and also apply the results for deep water. So you compare with both. Let's see which one is better.
I do the both data, the both calculations, and for the theoretical and experimental calculation is the similar in the deep water, and in the shallow water change a lot of.
So you can conclude something.
Yes, because for in the lab say that the shallow water activity.
I thought. See, the thing is this. Originally, we had worked with Giovanna preparing a different experiment, and we have really shallow water. We talk about 5 or 7 centimeters of water, and we were trying to push with a board the water, and the water would travel and return. And in that case, the water was really shallow. Then when we found out that the wave tank was working. And then we saw that, and there was a water depth of what? What was the water depth in the tank?
It's 20 centimeters.
Yes. So it looks like it's not so shallow anymore. So that's basically what you're telling me. I
Okay.
haven't done the numbers, but yeah, what you have to do is you can compare your experimental results with both ends. Okay, consider the information that we deduced in class, considering very deep water, and you can also include the results considering shallow water, GH. And then one of the things that you can tell us is that in that condition, okay, for the frequency, for the wave amplitudes that we have in our tank, 20 centimeters is shallow or is deep. So that's a good point for us, because from now on, we can take that. We don't need to fill more water, and we can think that, consider that's deep water, for example. So that's a good result.
Okay, doctor, thank you.
You're welcome. Any other question, people? It looks like, according to our authorities, that we have to be very careful. Okay, so if you need, you have questions, try to ask me or anybody else using this medium. There's no point in coming to the university. Okay, if you need some office hours, extra office hours, tonight I will be available at 8 p.m. It's basically for the people in the instructor's course. But if you have questions about the report, yeah, you can come and I'll try to answer your issues. Okay. Giovanna, please make sure that everybody knows the group number.
Yes, I'm sending an email now.
And please, you have to put that also in somewhere in Teams or in, yeah, in
Yes,
Teams.
it's in Teams.
Okay.
In the document called assistant.
Okay, good. In the next, how do you say pestaña in English?
Sheet.
Eyebrush. Bye-bye now.
You talk.
Thank you.
Okay,
Thank you,
bye
doctor.
now.